So back in the Middle Ages, alchemists were trying to transform low-cost metals like lead into gold. So they're like, we could become rich if we can do this. But they were never successful because all of their reactions were chemical reactions. And in a chemical reaction, elements do not change their identity. So they were doomed to failure, but they tried anyway. This is sort of, how humans are. In a nuclear reaction, though, we do get the transformation of one element into a different element, and this is known as transmutation. So transmutation, changing from one element into another, occurs in radioactive decay, which is what we talked about at the beginning of the chapter, and that is spontaneous emission of particles from a nucleus. This happens in fission, where we're taking a larger atom like uranium-235 and splitting it into smaller ones. It also happens in fusion, combining larger, small molecules into a larger one. There are other nuclear reactions that can also result in transmutation. So here we have nitrogen-14 getting hit by an alpha particle that will create oxygen-17 and release a proton. Aluminum can also be hit with an alpha particle and be turned into phosphorus. So in nuclear chemistry, the rules are a little different. So a lot of these nuclear reactions are done by bombarding something with a particle. Right? So, how do you turn nitrogen into oxygen? Well, you have to hit it with a helium nuclide, a beta particle. And you can't just toss these things. They have to be shot with high force. So how do we do that? This sort of research started back in the 1930s. Researchers built devices that could accelerate particles to very high velocities, which made more of these transmutation reactions possible. And so we're just going to briefly talk about a couple of these. A linear accelerator. In a single-stage linear accelerator, you get a charged particle that's accelerated in an evacuated tube by potential difference between the ends of the tube. It needs to be an evacuated tube because you don't want your charged particle running into, oxygen or something in the air. You want it to accelerate through essentially a vacuum so that you can get it out the other end without it reacting with something first. The Stanford Linear Accelerator, which is just over on the coast, is a multi-stage accelerator rather than a single stage. And so this is a picture of it. It's a really, really long building. I think it's like a mile long or something. So they can accelerate particles up to 90% of the speed of light, which is very, very fast. And when these particles collide with a target, they're going to produce a whole bunch of subatomic particles. And then these particles are studied. At the Stanford Linear Accelerator, researchers won the 1990 Nobel Prize in Physics for discovering evidence that protons and neutrons are actually composed of smaller particles called quarks. And so that's into nuclear physics and also or physical chemistry as an area that, some people are very interested in. How does a multi-stage accelerator work? So a single-stage accelerator, you would have one evacuated tube, and you'd have a voltage at this end and a voltage at that end, and that's one stage. Here what they do is they have multiple stages. So we have alternating voltage sources. So here we've got our proton source. We're shooting protons at the target. So initially, this is going to be negative to attract the proton. And as the proton comes in here, this switches to positive, which pushes the proton away, and this one is negative, attracting it. And so these are going to alternate in positive, negative charge to accelerate, cause the proton to go faster and faster through the tube. And then at the end, you've got your target, and you get a whole bunch of particles that you can look at. So those are linear accelerators. You can also have cyclotrons. So here we have alternating voltage applied between two semicircular halves. And this is a picture of a cyclotron. I think there's actually two of them here. So here we've got the particle moving in a spiral, basically. Well, actually, it's going this way. Accelerating it through this spiral using alternating voltage to hit a target. So the Fermi National Accelerator Lab is an example of this. It has two cyclotrons in a figure 8 configuration. Any questions? Yeah.
So in the multi-stage linear accelerator,
Mm-hmm.
is it the proton or the
Well, to do the accelerating, it has to be a charged particle. So in that example, it was a proton. So, I mean, you can shoot protons at things, you can shoot electrons at things, yeah, but it has to be charged in order to accelerate it with voltage.
They are in the gas state.
In the gas state. Mm-hmm. Yep. Yep. Any other questions?